What I want to talk to you about next are the periodic trends for electronegativity, ionization energy, and electron affinity. The reason I've decided to group all three of these together is not because I'm lazy. I think, that might be some of it, but I also just think it's convenient to think of these three together because they all three have the exact same trend for the exact same reasons. So just really quickly to refresh your memory, electronegativity is how badly is an atom going to hog electrons? How much is it going to want to steal them from the other atom? Ionization energy is how hard is it to pluck an electron away from something. Electron affinity is how bad does something want to grab another electron. So it kind of makes sense, if we think about this in terms of our video game analogy that we talked about earlier. Big Brother, the one that's more electronegative, is going to want to hog the video game controller more. He's going to want to take it. He's going to want to own it and have that high electronegativity. Well, it also kind of makes sense that if someone wants to hold on to that controller really tight, it's going to take a lot of energy to take it away from them. And the electron affinity, or that individual's affinity for grabbing the controller, is also going to be very high. So for that reason, these all have the same trends. They're not the exact same concept, but they get their trends off the basis of the same thing. So what I want to look at here is the lithium atom and the fluorine atom. Both of these are within the same row of the periodic table, or the same period. And let's look at what the differences are between them. Well, lithium has a 3 plus charge. It has 3 electrons. This should probably look familiar if you watch the last videos. I've done this before. So the lithium electron configuration will be 1s2, 2s1. So we can see from this that it's Z effective, its atomic number minus its number of inner electrons would just be 1. Fluorine, on the other hand, is a electron configuration 1s2, 2s2, 2p5. So it has 2 inner, and it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So it's the effective, the atomic number minus the number of inner electrons, 2 inner electrons, atomic number of 9, would be plus 7. So we can see that fluorine has a really high Z effective. Those electrons on the outside are being pulled towards it. And this really explains all of the trends above. So if fluorine's bound to something else, whatever it's bound to, whatever electrons are involved in that bond, are going to feel that strong Z effective, that plus 7 charge pulling those electrons towards it. That's why it has such a high electronegativity, and lithium is much, much weaker. As far as ionization energy, well, if those valence electrons are feeling a charge of plus 7 pulling them towards the center, so they're being pulled inward towards the nucleus, it's going to be really hard to try to remove one, try to take one of those valence electrons and just steal it from fluorine. It's going to be very difficult. It's going to be much easier for lithium, where that valence electron is just feeling a plus 1 charge. And electron affinity, well, again, it all goes back to that effective nuclear charge. With a effective nuclear charge of 7, fluorine is going to want to attract electrons. It's going to want to bring things in, whereas lithium really isn't going to want to do that. So for all of these reasons, fluorine has a higher electronegativity, higher ionization energy, and a higher electron affinity than lithium. And we can really generalize this and say that all of these trends increase from left to right, because the Z effective increases. So that's the example for that. Now what I want to talk about next is, I'm going to draw a picture here really quick and then resume the video. Alright, so here are my two, my lithium atom and my potassium atom that I'm going to be looking at. Lithium has a charge in here of 3 plus. Potassium is going to have 16 more electrons, so it's going to have a charge of 19 plus in the center. So again, we want to keep in mind effective nuclear charge as well as the principal energy level when considering any of our trends. So the principal energy level, let's look at lithium. Let's draw the electron configuration. It would be 1s2, 2s1 as we saw above. For potassium, this one's going to be a little longer. I'm just going to write it out here really quickly. So this potassium, the electron configuration bit. Well, what we can see for both of them is the Z effective is 1. 3 minus 2 would give us 1, and in this case we would have 19 minus 18, so the Z effective here would also be 1. So this can't be used to account for the difference, so what must it come down to? Well, if it's not the Z effective, it's the principal energy level. I'm just going to draw in the valence electrons here. So lithium's valence electron is in the N equals 2 energy level, whereas potassium's valence electron is all the way out here in the N equals 4 energy level. N equals 4 valence, N equals 2 valence. So the best way to think about this as far as the ionization, the electronegativity, the electron affinity, if these both have the same Z effective, what's going to account for the difference is the distance. How far away is this valence electron or this valence electron shell from the nucleus? How far away it is and the effect it has on all of these trends can best be thought of as if you have two magnets. So let's say you have two magnets and you're holding them together. So here's our guy, and he is holding whoops. I'm going to try to draw this stick figure guy again. He is holding two magnets. I'm clearly not an artist. And one magnet is in this hand. Let's say it's a very strong magnet. So there's our magnet. And the other magnet is in this hand right here. I'm going to refrain from drawing in future videos. But when these two are very close to each other, so remember magnets, you played with them in 8th grade, it's very hard to pull them apart when they're very close. You can feel the force between them when they're being held. So this guy's holding the magnets close, and maybe he's furrowing his brow here. He's having a hard time with them. On the other hand, if the magnets are further apart, let's say he has them, one's being held over here in this hand, and the other is being held over here in the other hand. Well, again, very awkward, very bad drawing. Definitely not artistic. Well, this guy's he's got a big smiley face on, so it's a smiley face right there because he's happy because he's not straining. Those magnets are so far away from each other that he doesn't really feel the force. The same can be said about this valence shell electron and in potassium, which is very far away, as opposed to that in lithium, which is very close. Because that valence electron is so far away for the potassium atom, it's going to be relatively easy to pull off compared with lithium. So it's going to have a much lower ionization energy than lithium does. On the other hand, or I guess on that, continuing on that logic, the electronegativity and the electron affinity are also going to be considerably lower for potassium than they are for lithium, because its valence shell is far away, so that pool of electrons is not as great.